Okay, so last class we finished our discussion of online learning problems, and when we mainly focused on the multiplicative weights update method, and we saw an application of that to boosting, which itself is kind of a classical question in learning theory. And then we started talking about PCA, right? And the motivation we said was you want to kind of find better representations of data, right? So today what we're going to do is kind of formulate the question of principal component analysis, or PCA, in a mathematical quantitative way, and then start discussing how to solve it, all right? And a couple of announcements first. Assignment 2 will be out today at 6 p.m. on GradeScope. And as usual, it will be due 1 week from now, which is next Wednesday at 10 p.m. And as I announced earlier, office hours, instead of being on Monday, they will be today from 3 to 4, all right? Okay, so okay. So we said, the idea behind principal component analysis is to identify directions along which some of data varies the most in descending order. We'll use this to do feature selection or dimension reduction. And once you have it, you can use your, standard learning analysis as you were doing before, right? So you have a high dimensional data set, a bunch of vectors, n vectors, very, very wide. If you think of something like genomic data, then maybe you have the genomic data of 10,000 individuals, but then each individual, the sequence is like millions of strings long, right? And you compress this or kind of reduce it to a low dimensional data set, where each x1 goes to something like x1 tilde or approximation, which is sitting in a much smaller dimensional space, all right? And there are many applications, compression, better accuracy in downstream tasks. But let me show you one specific application to revealing hidden structure in data. Again, this is this famous sort of illustrative experiment by the company 23andMe, which is a biotech company, where you can send your DNA and they'll sequence it and tell you some things about it. And they did this study on genes and geography. It's kind of a very perplexing finding, but it's there. So let's see what they found. So they collected genetic data of 6,000 individuals, all right? And you can map these gene sequences to vectors. In their case, they map the sequence of each person to a vector based on some kind of standard processing that they have. And each vector was 100,000 dimensions. Okay, so if you think about it, you have 6,000 individuals and you have 100,000 dimensions. That's a very, very wide matrix. If you want to do any data analysis on it, it's going to be hopeless because you'll end up doing overfitting, right? Okay, but they didn't even want to do that. They were doing something else. So first, these 6,000 individuals were not just any random people. They chose people who were kind of geographically localized, meaning they chose people, all of whose 4 grandparents were from the same sort of local neighborhood. Okay, if you're in Switzerland, then this was the person. They're all people from Europe, and they chose people whose all 4 parents kind of were born and grew up in the same sort of nearby areas. Okay. And then they did what kind of a weird thing, which is you have this high dimensional data, 100,000 dimensions. They extracted just the top 2 principal components, right? So when you extract the top 2 principal components, what happens is each individual now is just 2 numbers, right? You have 2 dimensions. You're extracting 2 PCAs, coordinates. So it's just 2-dimensional vectors. And they plotted these 2D points. Okay, they scaled the coordinates so that they kind of fit within like a map, and then they plotted them. and they colored these people's origins by country. Okay, and this is what they found. Kind of the resolution is a little bit short, but okay, so this is the 2D map of the individual and the country they belong to. Okay, and you can see there's a strong correlation between this and the actual map of Europe. This was drawn without any, without looking at their actual map or anything, right? You just have the genetic data, you extracted the first two principal components and put them on a map. So when you put them on a map, all people from Portugal somehow clustered in the same place. All people from Spain clustered in the same place, but also right next to Portugal. Same thing for France, Switzerland, Germany, Ireland, I think. Yeah. Denmark, 80 is what? I forget. Austria, yes. And you can see Italy going all the way here, right? Even the islands are there, Cyprus. Okay, Greece and Belgium, Romania, Hungary, Czech Republic. Okay. So even in this unsupervised data set, by putting points together, you can see some kind of correlation. And the correlation here is geographic, right? If you think about it, why would expect such a strong sort of geographic data to be embedded in your genetic data, right? But it's there. Okay. Any questions about this? Kind of a surprising find, right? It just extracted the genetic data. Of course, if you just took people who are not from the place, then it wouldn't make sense. That's why they kind of selected individuals whose 4 grandparents were kind of from the same locality. Okay. And beyond this, if you actually dig deeper, even, further fine-grained details were present just in this principal component map. So if you look at people within Switzerland, Switzerland has the Swiss-speaking part of Switzerland, there's a German-speaking part of Switzerland, there's the French-speaking part of Switzerland, there's the Italian-speaking part of Switzerland, corresponding to which side of the country you're on. So the people from French-speaking Swiss were all kind of clustered towards the border with France. The people from the German-speaking part were all clustered towards the border with Germany and so on. Okay. So even the sort of finer details within each country were present in the genetic data, and you didn't have to do some very complicated analysis to see it. You had a standard way to map genetic sequences to vectors, and once you have that vector, it was very high dimensional, so they just took the first two principles. Okay. Yes. I mean, maybe, but I guess they were trying to also show like a visualization, right? They wanted to show that if you just put them on a map, you were right. Maybe if you go to higher PCs, you'll see that people within sort of the same locality have higher correlations, but even just looking at it in the map is very visually striking. It's the best way to see the impact. In fact, that sounds more believable that they would be correlated. But what's perplexing is not only that they're correlated, but you see the actual geographic distances showing up, right? There's no reason geographic distance should have anything to do with whatever is happening in the genetic markers, right? Okay, so so this is just to illustrate the power of PCA in some simple context, right? And that's one reason why it's often the first step, even before you start doing supervised learning. So even if you have supervised data, in many cases, like when you're very, very few samples compared to the dimension, you're in a very high dimensional space, then doing PCA is a good first step, right? So ubiquitous tool, you can get better accuracy in downstream tasks, you can reveal hidden structure as we saw, right? Just the genetic data is enough to capture geographic information and so on. Okay. All right. Any questions about this particular sort of visualization of the power of PCA? Okay. So let me now talk about another sort of effect, another sort of simple application of PCA, and this is for clustering. So one of the uses of PCA is for clustering, right? Which is, as you were saying, maybe if you go to higher and higher PCA components, it will identify which points should go together and which points should not go together, right? And let's say in this, this is called the latent semantic analysis or document analysis. Now we are viewing each document as a vector. We have a bunch of text documents, and you can view each document as a vector of how many times each word appears in it. Okay. So maybe document one is, you have these letters, and then you just count, okay, the letter A appears 100 times, the letter B 98 times, and so on. Okay. So if you think about it this way, once again, you're in a very high dimensional data set, right? Because each coordinate, each potential word corresponds to a coordinate, right? Even if you have 100 documents, each has 10,000 words, then the number of vectors is 100, but the dimension could be 10,000 times 100. Okay. So each document is a high dimensional word. So often, at least for some tasks, it makes sense to just do like extract principal components and then use that as kind of a compression of each document. Okay. And okay, so let me illustrate this for sort of a very dummy data set, but again, just as a proof of concept rather than something that you would actually use in the wild. So what I talked about is called latent semantic analysis, right? Where you're viewing each document as just a bag of words, meaning I'm just going to count how many times each word appears, and that's going to be my representation of each document, right? And there are standard tools within, like, pretty much any ML library to extract such things. And I should also point out that PCA, of course, is such an important tool that every language has its own implementation for it, right? So you don't have to sort of even know how it is done. You can just call a library to do it, but we will dig into it, how they do it anyway, because we want to modify it. But for now, let's say, I have I'm taking a data set here, which contains some number of documents from New York Times. These are just review articles of various pieces. And there are two kinds of reviews. Those are, some of them are art reviews and some of them are music reviews, right? Some stories are about, okay, this is a painting that I'm reviewing, or maybe some drama, and some things are just about music, okay? And you have all of these documents. Each document has a label. It's either a review of an art review article, and then you can count how many times each word appears normalized some way, all right? So there are 4,000 columns, meaning there are 4,000 words, and the number of documents is basically about 100, okay, 102. So again, it's a very wide matrix. There are only 100 rows, 100 sort of documents, and 4,000 columns. Okay. And this is the class label count. The number of art documents is 57, 45, so roughly 50-50 split. Okay. And what I want to do is, once again, not do much, just apply PCA and see what happens, right? You have 100 documents sitting in 4,000 dimensions. For each document, I'm just going to extract the top 2 principal components and plot it, right? And I'm going to do this without the class labels. So you can remove the class labels, extract the PCA. And as I said, PCA is such a ubiquitous tool that you can just sort of call a library for it. Like, there's a PCA, you can say PCA.fit, and it will find the components for you. Okay, there's not much you need to do after that. Okay, you can get PCA, the principal components. And now each document will just become two numbers, right? So once you're going from 4,000 dimensions to two dimensions, so each document is just two numbers, and you can check if the two principal components are perpendicular to each other, right? So remember when we intuitively defined PCA, we say you pick a direction, and the next direction you want to be perpendicular to the older direction, right? And even in this sort of rudimentary implementation where you're just calling the library, you can check that the dot product is 0. Okay. All right. But what's interesting is what happens if I just plot the principal component. Okay. And if I plot the principal components, you can see some kind of nice separation that's happening between the art and music dots, right? So all the red ones are all art pieces. I mean, there are a few scattered ones over there, but most of the red ones are kind of, if you draw, you can easily separate them with a line, right? If you draw a line, then the music pieces will be on one side and the art pieces are on the other side for the most part. There'll be some error, but you can clearly delineate some structure at least. Okay. So once again, you didn't have to do anything sort of complicated. Just call the PCA, plotted them, and you can see some kind of clustering happening. All right. Any questions about this? Yeah. Mm-hmm. I mean, it depends. Like, sometimes PCA might not even be the right tool. Like often it is when you think there is some sort of linear separation or something. Otherwise, you would do something like kernel PCA where you would transform and then do a PCA and other things like that. It has more to do with what you think about the underlying distribution, right? But by and large, I would say that most data would the structure would be revealed by a PCA, at least after some kind of transformation. Maybe not with the straight features, like we were lucky in these two cases that you didn't have to do any pre-processing. You just applied PCA on the raw data and you saw the structure, right? Whereas if you're taking images, then maybe you'll apply some filter, so that gives you a new representation, and then you do PCA on the new representation, right? So that's a way to kind of further find a more sophisticated use of PCA. Okay. It has less to do with the dimension more than like what you think about the distribution of the data. Okay. Any other questions? All right. I mean, there are many other examples like this. I mean, of all of this, I find the 23andMe one the most striking because there should be, a priori, there should be no reason why sort of genetic correlation should correspond to exact geographic distance as we see on the map of Europe, but it's there. Okay. All right. So those are some ways in which you can use PCA. But now let's go back to what it is, how to formulate it, how does one find these principal components, and then why do we need to know how to find those components if you can call the libraries directly? All right, so we'll talk about those things. Okay. And so I'm going to motivate PCA by first talking about a very sort of simple question, and then we'll generalize it to the more general problem. Okay. And the question is the following. Call it the best fit line problem. And the idea is as follows. Okay, imagine you have a high dimensional data set or some dimensional data set, and you want to sort of represent all of the data set using only one dimension. It's just a single feature now, right? And so in some sense, like let's say this is your set of points. Like let's say you're in 2 dimensions, but you want to pick out even a single dimension instead of using 2 dimensions. So which sort of direction would you pick to represent the data here? Right? And visually it seems like you should pick a line like this and then use that as your coordinate basis, right? That seems to make the most sense. Okay. And intuitively, you could argue that that's because somehow this line approximates the data well. Okay, if you think of all possible lines that could approximate our data in some sense, this line seems to do the best job. Okay, so that's what motivates this best fit line problem. And so let me say the input is a bunch of points, x1 through xn in d dimensions, and our output should be find the line that is closest to the data set. Okay. We have these points. I want to find the line that is closest to the data set. And we have to define what closeness means. And we kind of know what a line is, right? It's just a single dimensional vector space. And we have to decide what is the notion of closeness we should use. Okay, so let's say okay, so any suggestions on how you could potentially define closeness? Like just draw a line which somehow approximates the data set the best. What would be a quantitative way of measuring closeness? Any suggestions? Yeah. Okay. So that makes sense, right? Essentially for each point, check how far is it from the line, right? Like, if you take this point, for example, it's on the line. So, it's perfect. If you take this point, somehow the distance is more, maybe not as good. This point again is very close, it's good, and so on, right? So a natural thing to try is to minimize aggregate distance. Right? Once again, you have many points. You have n points, so you should not just focus on like how far is a single point. Just aggregate the distances of all the points and somehow try and find a direction which minimizes this aggregate. Okay. Well, I mean, that sounds good, but still we had to define what distance to use, right? And to think about what distance to use, let me maybe sort of zoom in on this picture and say you have something like this. You have a bunch of points maybe. And if I draw a line now, something like this, right? I can define the distance. The natural notion is to look at how far each point is to the closest point on the line, right? Now, the closest point to this would be something like this. So I would measure the length of this line segment. Maybe let me use red. Right, so right, it's the length of these sort of, error, or how far each point is from the line. That's what we should count. Okay. And there is actually a name given a point in the line. There's a name for the point on the line which is closest to it. What is the name? So like if I give you this and I want to find out, okay, what's the closest point onto the line? You call it the projection, right? So this is the projection. And if I call this point x, projection of x onto the line. Okay. So projection of a point onto a line, or more generally a subspace, will be the closest point within the line of the subspace to the within the line of subspace. Okay. So let's see. The projection of the point x onto the line L, right? So this would be projection onto L of x is the closest point on L to x. Okay, and closest means it measures the distance in the usual Euclidean sense, right? So meaning projection L of x is the point on L that minimizes okay. So just the length of the line segment. Imagine, for every point, which point has the shortest line segment, that would be the projection. Okay. Any questions about this? All right. So if this is your notion of projection, then what are you looking to minimize, right? You're looking to minimize the aggregate sort of distance of points to the line, right? So meaning what you're really interested in is qualitatively find a line L that minimizes aggregate distances, that is right, because projection is the closest point, but how far is the line segment? What's the length of the line segment? It's x, the length of x minus the projection. Okay, so in some sense what you're saying is, okay, for each point x, I'm going to replace it with the projection onto the line as my approximation. Okay, so each x now will be replaced with this corresponding projection, kind of a compact one-dimensional representation. And then I need to measure the error. So the error is how far are these? If your point is already on the line, you're very good. If your point is very far, then you're going to incur high error. All right. Okay. So we are almost there, except there is one twist. So if you had to aggregate distance, then you would define average distance of L as actually let's not distance of L as look at all the points in your data set and measure how far is each point from the line. Okay, does this objective make sense? You're looking at like, how far each point is from the line, and then you're adding up these distances. All right, seems fairly natural. Okay, but this is not the one that you should use. You should actually look at the sum of squares of the distance. All right, and that's, I mean, why squares versus the other thing? It's kind of it's a very important term. Without this, it becomes the problem becomes very hard to solve. With the square, you can use some nice tricks to solve it. Okay. And there are also some good statistical reasons to measure, to aggregate things by sum of squares instead of just the sum. Okay. It's a little bit like saying, don't use the L1 norm or the absolute value, but use the square of the difference as the error. All right. So this is going to be our definition of distance, okay, where projection L of x is closest point on L to x. Okay, all right. So now we have our best fit line problem. So input is a point, set of points, that's our data set. And our goal is to come up with an algorithm which will take the set of data points as input and gives us output a line L that minimizes maybe let me put something like this if there's ambiguity. And actually, let me just say error L comma X, right? It really quantifies how much error you would get if you represented every point by just projecting onto the line L, right? So given your set of points, and our goal is to find me the line that minimizes this notion of error. Okay. So we started out with some statistical thing that we wanted to do, and now we have just an algorithmic question. Given the set of points, solve me this optimization problem. Kind of an odd looking optimization problem because somehow you're optimizing over the space of lines. So you have to decide, okay, how to parameterize that. And then, you have the sum of squares, which is, as I said, y squares and not just the sum. Well, one reason is that squares makes it an easier problem to solve. Okay. Any questions about this? So going back here, pictorially, you're likely to pick this line over this line. And if I pick the cross line, then most of the points are very far, so that would have a worse performance. All right, okay. So that's the best fit line problem. But in general, you might not just be interested in a single line, right? A line gives you one parameter to represent each point, but maybe you have more flexibility. You don't have to go all the way from whatever 100,000 to just a single number. Maybe you have more flexibility. Okay, and this leads us to the general best fit subspace problem. Okay, or BFS for now, right? And once again, you're given as input a set of points x1, x2 to xn in RD, and an integer K, which is greater than or equal to 1. Okay, K corresponds, roughly speaking, to how much, what's the dimension of the subspace you're going to use, right? How many numbers are you allowed to represent each point with? Okay, and for any k-dimensional subspace, now a line is just a one-dimensional subspace, right? You're taking a single point and scaling it in both directions. That's how you get a line. And a k-dimensional subspace is you're taking 2 points or k points and then taking the span. Okay, if I take any k-dimensional subspace, I can still define this notion of distance and error. Okay, for each point, check how far is the point from the subspace, right? And take the sum of squares, and our goal will be to find a k-dimensional subspace S that minimizes the error. Okay, so I mean, if you let's say maybe your points are in 3 dimensions. Okay, and you're allowed to approximate it with a plane. Okay, so your points are in 3 dimensions, but you're allowed to pick a 2-dimensional subspace, meaning a plane, and you're approximating each point with this projection onto the plane, right? So something like this. This is S, each point X goes to a projection, and then you're checking these distances. Okay, can now imagine playing this out in higher dimensions. You have 1,000 dimensions, but my K is 3, 4, and just approximating it using this and proceeding. Okay, so before going further and trying to talk about algorithms, we need to decide how are you going to represent something, right? So the output I said should be find a k-dimensional subspace that minimizes it. So what does it mean to find a k-dimensional subspace? How would you represent a subspace? What would be a nice way to represent a subspace? Yeah, find a k basis vector, right? So if you want it to be more concrete, I will say your output should be k vector. You'll say maybe they're orthonormal just to be kind of even more concrete, and say, okay, your goal is I give you the set of n points and return me a set of k orthonormal, return a k orthonormal vectors that form a basis for S. Okay, so how are you going to represent the subspace? You're going to return me like a basis for it. So maybe in this case, like for the diagram here, I might pick okay, maybe the basis is something like this. I might return these 2 purple directions and say, okay, this form this span, this form a basis, and that's the best test. All right. Okay. So we have the computational thing set up, and now let's go ahead and try and solve this problem. All right. Okay. So before going ahead, what we're going to do is first solve the problem for the simplest case, which is k equals 1. Okay, and then we'll see how to, it's a miracle of nature that somehow nature was kind to us. Solving the case of k equals 1 also tells you how to solve the higher k case, as we'll see. Okay, so the next goal is how to solve k equals 1, right? Okay. And so to do that, we need to review some linear algebra, basically around the Pythagoras theorem, okay? And so let me do this once so that, it'll be clear whenever we use it later on. Okay, so maybe do this, okay. So I'm going to draw it in 3 dimensions. Okay, so think of, this is a 2D plane tilted at an angle. Maybe I can something like this. Is that any better? Yeah, better. Okay, so this is the origin, and maybe there is some point x in 3D, and you can project this point onto S, right? So this is projection onto S of x. This is our okay, and this is the error, right? Okay. And okay. So first things, as we said, kind of almost from definition, the projection of x onto S is the closest point within S to x, right? Among all the points in S, which point is closest to x? That's going to be the projection. Okay. And the other thing is, if you think about it geometrically, you have here 3 vectors, right? Maybe let me draw. Okay, you had the original vector x, you have the projection vector, and you have the error vector, which is the difference between these two, right? So no matter what your subspace is, no matter what your x is, you can say something about this diagram. And what is that? What is this triangle? Well, what should this angle be here? A right angle, right? So no matter where you are, whatever space, how much of a dimension you may be in, these 3 points, like, x minus projection of x, will be at a right angle to the projection vector. Okay. So this is 90 degrees. Okay. So angle between the error vector and the projection vector is 90 degrees. Okay. I mean, you can actually prove it geometrically. If it's not 90 degrees, then you can find a closer point. If it's like, and if it's 90 degrees, that's when you cannot make further progress. All right. And if you had to write this condition linear algebraically, what would it translate to? If 2 vectors are at an angle of 90 degrees, then what can you say about them linear algebraically? Yeah. The dot product is 0, right? angle is 90 degrees in sort of more angle is 90 degrees, what you would say in, maybe high school. If you're in college, you would say the dot product is 0, right? So we come up to this condition, which is the dot product between these two vectors is 0. Okay. And finally, we have the Pythagoras theorem, right? The length of x should be the length of the hypotenuse, should be the sum of the square of the length of the hypotenuse should be the sum of squares of the two lines, right? So because it's in a right angle, you would get that the length of x is exactly the length of the projection of x squared plus the length of the error vector. Okay. And in fact, this identity is why you use the square and instead of just a single, the length in the definition of our error function. All right. Oh, Pythagoras. Okay, so far so good, but there is one additional property which maybe is okay, so one additional property. So this is only talking about x projection of x onto s, right? You're only talking about those 2 points so far. But what if I take, maybe some other vector, let's say u in s. Okay, this is a vector which is in this slanted plane. Okay, let me not make it so easy to see. So okay, this is still in the same subspace. What can you say about this vector u and any of the other vectors? Is something always true still? In particular, what can you tell me about this red vector and any vector in the subspace? Right, you have the plane. I want to say that the red vector is perpendicular to it, right? So it's perpendicular not just to this direction, but actually to the entire plane. Right? You have a plane, you have a point, and when you project it, the error is perpendicular to every vector in that plane S. Okay? So in this diagram, like for instance, not only is the red vector perpendicular to the orange vector, but it should be perpendicular to any vector in the yellow shaded region. Okay? So that's the fourth property that we will use a few times. Okay? So for all u in S, u is perpendicular to the error vector. Okay. Concretely, for all u in S, the inner product of u with the error vector is 0. Okay. All right, so let's keep these 4 properties in mind, and then we will play with them to get to our algorithm. So that's the linear algebra detour. Now let's get back to our algorithmic question, which is, okay, I give you this input, a set of points x1, x2, up to xn, right? And our goal was find a line L that minimizes Okay. Now let's just sort of play with this, right? So by the Pythagoras' theorem, we know that the error vector is the difference of the actual length minus the length of the projection. Okay. So let's put that in here, and you get this is the same as okay. Now this is the same as okay. Now the advantage of writing it this way is that this is a quantity that doesn't depend on L, right? It just depends on the data set. It doesn't depend on which line you're picking, right? So you have much. So minimizing the error is the same as, so this doesn't change based on L. So minimizing the error should be the same as doing what to this? Where you're subtracting something, right? So you want to minimize after subtracting means you want to maximize this, right? Is the same as maximizing okay. So let me give this quantity also a name. For any line L, as we define the error to be the length of the sum of squares of the error vectors, let me define the variance as sum of squares of the projections onto the line. Okay. Intuitively, if the point is actually in the subspace, then both of them will agree. So the projection captures almost all of the content of X, right? That's kind of the rough correspondence. The two things are very close, and the projection is capturing maybe all of the information of X already. So it should be maximizing the length and so on. Okay. So the takeaway is that minimizing error, this works not just for lines, it will work for anything. So minimizing error over k-dimensional subspaces is the same as maximizing the variance over k-dimensional. Okay, so you're trying to find a subspace which explains, quote unquote, explains as much of the data as possible. Meaning, when you take the projections, their lens capture as much of the information as possible. Okay. All right. So what we're going to do next is, while statistically speaking, the notion of minimizing the error is easier to motivate, but for computational purposes, maximizing the variance is a better quantity to work with. Okay. So what we're going to do next is kind of focus on maximizing the variance for k equals 1 and then connect it to something else. Okay. All right, let's take a 5-minute break, and when we come back, we'll talk about how to maximize the variance along a direction. Because I forgot to announce at the beginning, so the new I started a new Scribble node for this module because the old one is getting too big and kind of slow to load. So go to the course web page to find the link for the new one. And okay, so where were we? We have to solve this maximizing the variance problem now. And let's try and do this for dimension 1, right? And what we'll do is solve it in the sense that we'll find a more succinct way to formulate it and then see how to use it. We will solve it later on. Okay. All right. So how to find a line that is dimension 1 subspace that maximizes okay. So, let's say your line, you have to specify it some way and specify it as span of a vector. Yeah, I want a vector V such that, its span is going to, that's the direction of the best fit line. Okay, maybe U is somewhere here, or V is somewhere there. And that determines the direction along which you're trying to maximize the variance. Now, so recall, so variance of L and X is okay. Now, what is I want to say that there's actually an equation for what the projection of X onto V is. It is pointing along the direction of V, right? That's for sure. But how far along should you go in this direction? What is the length of this? Any guesses? What's going to be the length of the projection of X along the direction V? Yeah. Right, but I think there's a more compact thing that you can do when you have the actual vector, right? Like, let's say I give you a vector, which is, I give the coordinate representation and I give the coordinate representation of V, then you can write this down exactly. Yeah. Exactly, the dot product, right? So the length of this can be obtained by the cosine rule. In particular, for a single sort of the projection onto, let me use L here, of X is X comma V, right? And that's true if V is a unit vector. Right, so the length is going to be the dot product, which basically depends on the cosine of this angle, right? If V is a unit vector, then that's just the dot product. But if it's not a unit vector, then I have to scale it to become a unit vector. Okay, so that's why there is this guy here, right? So this point will be the length is the dot product between X and the unit. Oh, here, yeah. Right. So the length of this is exactly this much, so the length is going to be this much. Okay. All right. So I can write this as, Xi inner product with V square divided by the norm of V square, right? So I can further write this as this guy. Okay. This seems a little cumbersome to write down. Once again, there's a compact way to write it if I can connect it to matrix representation. Right. So given my data set x1 through xn, let me form the matrix X whose rows are exactly my data points. It's an n by d matrix. Right? Where each row is exactly the, the first row is x1, the second row is x2, and so on. Then if I multiply it with the vector v, what do we get? If I take this matrix X multiplied with the vector v, we did something like this before when we talked about least squares regression too, right? So what you get here is going to be exactly these inner products, right? So maybe do something. So this entry is going to be x1 comma v. The second entry is x2 comma v, and so on, right? So compactly, I can say the variance of S in X, where S is, recall, span of the direction V, is just okay. Take your matrix X, multiply on the right with a vector V, and try to maximize the length of this matrix vector product, up to normalization by V. Okay. So, let me just sort of say, what did we learn by this symbol manipulation? We could write the variance as something like this. Okay, where S is span of V. Right? So solving the best fit line problem is equivalent by our series of deductions to the following. The best fit line problem is equivalent you had to minimize the error, which is the same as maximizing the variance, which is the same as finding a direction V, which maximizes this ratio, right? So it's equivalent to find me the direction V, find V that maximizes okay. And I mean, the ratio is kind of scale invariant, right? If I find a V, then 10 times V would also be a solution. But if I look for the unit norm, solution to this problem is called the first right singular vector of the matrix X. Okay. It's also called the first principal component of X. Okay. Among all the vectors, we find one which has unit norm, and that's called both the first right singular vector of X as well as the first principal component of X. Right? When we still haven't discussed like how to find this vector, but at least we have some kind of compact way. Finding the best fit line is equivalent to solving this optimization problem, which the solution to which has a name. All right. Okay, let's do a couple of examples to maybe get some intuition. Okay. Suppose your X looks like this. Maybe it has 10. Suppose your X is a matrix which looks like this, in the sense that all of the columns 2 to the end are all 0. What's going to be the first principal component of X? Any guesses? Yeah? Right, so it should just be the vector which has 1 in the first coordinate and 0s everywhere else. Right, so this is going to be your V. I mean, makes sense, right? Like all of the information is there in the first coordinate. So if I project along that, you should get the max information. So X times V would capture all of X norm. Okay. Make sense? All right. Okay, so that's sort of one sort of example. And here's maybe a slightly different looking example. Okay. Maybe there's a vector U and all of the things, this is a unit vector. If your matrix X looks like this, what's the first principal component going to be? U, right? Again, because if you think of these points, they're all proportional to U. So they're all in the direction of U. So if you pick that line, of course, you'll just find maximum variance and minimum error. Okay. And you can kind of play with some simple examples to get a sense of this definition. All right. Okay. So imagine we can solve this optimization problem, which is, given a matrix X, someone told you, okay, I can give you the vector V, which maximizes this inner product, which in turn will give us the solution to the best fit line problem, or the, first principal vector, first principal component, and the first right singular vector. Okay. So all of this applies only for one line. But how about the two-dimensional case? What if I want to solve the best fit subspace problem for dimension 2? So recall, what are we trying to do here? We want to minimize find me a two-dimensional subspace X, which minimizes this, the sum of squares of the error vectors, or equivalently maximizes okay. If I told you how to solve the k equals 1 case, does it give you a handle on how to solve the k equals 2 case? Right? You have to find two directions which together could explain the data the best. But what you can do so far, let's say, is you can find a single direction which does the best. So if I give you that power, what would be something that you could try? Yeah. Right. So, I mean, like a natural thing to try would be to use a greedy approach. Right? Meaning, you find the first principal component using whatever sort of method you have. And then find first principal component of the leftover portion. Okay. So the first principal component gives you some approximation, right? And it makes sense that, for the next step, you would focus on the errors and then try to approximate the errors using a line. Okay. So let me maybe draw a picture. Actually, let me try and code it up as a pseudocode, and then we'll see. Okay, so what's the idea? Find first principal component. Let's say that is V1. Okay. Now you replace each xi with okay. So intuitively, what you're saying is, okay, you have your bunch of points. Let me draw it in 3 dimensions. And okay, I found the best fit line, and maybe it looks something like this. Okay. So the line has some approximations, right? Think of for each point, I have this projection here, I have this projection here, this projection here. Okay. So in some sense, this line takes care of this component, right? For the next step, it makes sense to approximate the error, right? It's like saying, okay, the first step got me somewhat close to X. For the next step, whatever is left over, I'm going to try and get the best possible approximation to that. Okay. So find first PC of the new data set. It's like saying, okay, you got some errors. Now for the second step, try to approximate the errors using the same method. Okay. That's one greedy approach. What's the other approach that you could try? Okay, let me call it idea one. This was one suggestion. Kind of, you approximate the errors and then you kind of repeat the same process. What else could you try and do? The other thing you could try is what we discussed, like, yesterday, right? You found one direction along which you had maximum variance. For the second direction, maybe you should pick something perpendicular to it, right? So try and maximize the direction, maximize the variance again, but this time, just focus on directions which are perpendicular to what you already found. Okay. So the second step, idea two, is find first PC V1, then find direction maximizing find the direction which maximizes the variance, restricted to all those directions perpendicular to V1. Okay. If I drop this, obviously it will give me the same answer as V1, but if I pose this perpendicularity condition, then I'm asking it to do something non-trivial. Okay. So that is find V2 to be argmax all right. So both of these are kind of natural greedy algorithms you could try. Okay, so one is kind of more of a direct reduction because you're just sort of applying the same algorithm here, but then somehow here it seems a little different because you have to do this orthogonality. Yeah. Yes, I mean, intuitively it's just like, okay, I already found something which explains the data somewhat, and I don't want any redundancy. For the next direction, if it has some kind of overlap with this direction, maybe I'm not making the best use of it. Right, so find something which is not explained in this direction at all, and then that corresponds to orthogonality. Okay, that's kind of one intuition. The sort of more technical thing would be that to think of all of this orange vector, right? They would all be perpendicular to this direction. Right? Remember, we said the error vectors are actually perpendicular to everything in the subspace. Right? So they would actually be perpendicular to this direction V1. So when you do PCA, you'll automatically end up working in space perpendicular. Okay. All right. So there are two potential ways of going to the next step. Either you take out what you found and then do the same thing again, or try and find the direction which is perpendicular to what you already found. Okay. And it's kind of, as it turns out, it doesn't matter which one you choose because both will give you the same answer. Okay. And just for concreteness, we are going to pick one of these things. And I'm going to write it down. So the second right singular vector or second principal component of X is essentially any vector where the norm of V is 1. Again, this kind of normalization so that okay. And perpendicular just means that the inner product is 0. Okay. The second right singular vector is defined as the direction V, which is perpendicular to the first singular vector and maximizes x times v square. And it takes a little bit of work, but you can show that this is the same as actually solving this problem. Yeah. Sorry, there's a lot of noise here. Can you say it again? Yes, exactly. Right. It's harder to enforce orthogonality, right? So you would actually implement this idea by doing, subtract it out and then doing the first PC again. Okay. The first idea is nicer because you're reducing it back to the same question on a different data set. So if you had an oracle for finding the first PC, then you just keep calling it after this modification. We'll get to that. Yeah. Okay. All right. Okay, so now that we have these things, we can define not just the second singular vector, but also the third singular vector, the third principal component using the same thing. Okay? The good thing about the second idea is that it makes the extension to third and higher much more easier. Like, you don't have to say, okay, project things out and then take the first PC again. It's a bit more form-like, and you can say something like this. Okay. If I have already found the first, let's say, I minus 1 singular vectors, or the first, second, and so on up to I minus 1 right singular vectors. Then the ith one is defined exactly using kind of, the same thing. Find me a vector which maximizes x times v squared, but is now perpendicular to all of the ones that you already found. Okay. So I want this one to be perpendicular to v1, perpendicular to v2, all the way up to vi minus 1. Okay. And this will be the ith principal component of x, or the ith right singular vector. Okay. So, so far we defined some notion of singular vectors iteratively. Find one, find something which maximizes inner product. Again, subject to perpendicularity and so on. But what does all of this have to do with the best fit subspace solver, right? So in the question, you had to come up with a single k-dimensional subspace. It didn't say anything about, okay, the first one gives you the best fit line, the first two give you the best two-dimensional subspace, and so on. It said, okay, just find me the best k-dimensional subspace. And here's where I think, we just get lucky. Typically, greedy algorithms need not work for complicated problems, right? And if I ask you to find the best k things, it might not be a good strategy to pick the best one, then the best one, then the best one, and so on, right? But here, that actually works. The span of the first k right singular vectors actually minimizes, let me say vectors maximizes okay, the span of the first k right singular vectors maximizes the variance and hence minimizes the error and hence solves the best fit subspace problem. Okay. All right. And let me, kind of emphasize somewhat of the magic here. If we actually defined emphasize how lucky we were. When we defined the error, we took the sum of squares, right? Let's say we didn't take the sum of squares, we just looked at the average distance. It's kind of, I think it's still a natural notion. You're just taking the sum of the lengths of how far you are. So qualitatively, it still fits what we want to do. Find a line or find a subspace, which approximates the data as well as possible. Okay. If this is our notion, then finding the best fit line and then finding the best fit line of the leftover is not the same as finding best fit subspace with k equals to. Okay. Essentially, this theorem is saying, if you want to solve the best fit subspace problem when you have the sum of squares, you could find the best fit line, subtract that out from your data set, find the best fit line of what's left, subtract that out, find the best fit line of what's left, and you keep iterating this, you will end up with the best fit, 3-dimensional subspace, 4-dimensional subspace, and so on. So you can keep on incrementally adding things while always being the best. Okay. If I define the error without the square, this is no longer true. Like the sum of the square makes the thing work through. Without the square, it doesn't work. Okay. But anyway, there are also good statistical reasons to work with the square. So we kind of get lucky both on kind of an algorithmic front and statistical reasons. Okay. Any questions about the theorem? So the main point here is that you can find one at a time and then find that solves the best k-dimensional problem, even though, a priori it might not. All right. Okay. So what I will do in the remaining is sketch the proof of this result that the span of the first k right singular vector maximizes the variance, but I'll do it first for k equals 2. And you will finish the proof in the homework. Okay, so let me say here 1 span of first 2 right singular vectors solves the best fit Okay, let's see why such a thing could be true, right? So what do we want to show? We have V1, which is first singular vector, and we have V2, which is second singular vector, and then we are trying to reason about, let's say S is span of V1, V2, okay, so this is what we are trying to reason about, right? We want to say that this is maximized by our specific choice of the subspaces. Okay. But before talking about the specific choice of the subspace, we have to again do a little bit of linear algebra. So let's say this is the origin, and imagine I have some two-dimensional subspace. Okay, let me call it T, and I have a basis for it. Right? I have W1 and I have W2. Okay, so two perpendicular vectors which form a basis for my subspace T. The projection of X onto the subspace will have in the one-dimensional case, we had a simple formula for what the projection was, right? It was given by the inner product between the point X and the direction V, right? But my claim is, even in the two-dimensional case, you do have kind of a nice representation for the length of this projection. Can anyone tell me what's the length going to be? Yeah. Exactly, right? So basically, it's like if I have a three-dimensional point, when I project onto the XY plane, the length of the projection is going to be sum of squares of just the first two coordinates, right? And because W1 and W2 are perpendicular, we can do something similar, all right? So linear algebra fact. Okay, so because these two are perpendicular, I can essentially use Pythagoras' theorem within the subspace. Okay. Okay. So that means that variance S of X is I can think of this as Xi inner product with V1 squared plus xi inner product with v2 squared, okay, which I can succinctly write down as the norm of x times v1 squared and the norm of x times v2 squared, okay? So the score, the variance of the span of the two principal components is given by x times v1 squared and x times v2 squared, the sum of squares of these two lengths. Okay. All right, so this is good. But now what we want to say that this is the best you can get, right? So no matter what other subspace you pick, you cannot get a score higher than this. So take any other two-dimensional subspace. T with an orthonormal basis W1, W. I can pick, for any subspace, there can be many, many orthonormal bases. And I'm picking something here. And what can I say? The variance of t comma x, I can use the same formula. Okay, so we use the same equation twice. So, okay, so let me write it. So here we have the score of the span of the first two subspaces, and here we have the score of some other subspace. We want to say that that's higher than this. Okay. How can we compare these two? Any suggestions? Right. So at least from the definition, we know that the first number here is bigger than the second, this number, right? Because we said, v1 is a direction which maximizes the length of x times v1 squared, period, right? So this one is going to be bigger than this always. But how about these two? Those two we cannot compare directly, right? What if W2 is, aligned with V1? We only know that x times V2 maximizes the length among all vectors which are perpendicular to the first direction, perpendicular to V1, whereas it might not be true here. Okay, so while we know that this is bigger than this, we can't immediately say that the second thing in the sum is bigger than the second sum here. Okay, so we have to be a bit more careful in how we compare these two things, right? Okay, so the trick is, you have your subspace T, right? And let's see where V1 is relative to this subspace. Okay. The trick is that we get to pick which subspace, which basis to use for T. Okay. I can use any orthonormal basis for T and use the same formula, right? So what we're going to do in the next class is kind of find a clever choice of the basis for T to make this comparison apples to apples. We only know so far that I can compare the first term to the first term here, but if I don't do anything, I cannot compare the second term to the second. Okay. But there's a simple way to go around it, and that comes from the idea that if I look at the projection of V1 onto T, I can choose a basis where W2 is actually perpendicular to V1. No matter what subspace you have, no matter what vector you have, I can choose a basis where one of the directions is perpendicular to my fixed vector V1. Okay. So there exists a basis, there exists an orthonormal basis W1, W2 for T, where W2 is perpendicular to V1. Okay. Once this is true, we are done, because now we know by definition you should have this, right? By definition of first PC. And we should also have the second condition now. By definition of second PC. Okay. And this implies that variance T comma X is the sum of these two quantities is less than or equal to what we want. Okay. So the span of the first two singular vectors does maximize the variance among all of the two-dimensional subspaces. Okay. So when we come back in the next lecture, I'll review this argument again. But the trick is that you can choose the basis along which to use this equation. Okay. I can use the basis carefully, and that helps us make the calculation with the right way. Okay. All right. We'll resume next Monday, and remember that the assignment 2 will be out today at 6.